Well, hello and welcome to another episode. It's great to see you all. I hope you're doing well. As this is my first proper episode of 2021, allow me to take this opportunity just to wish you all a happy new year and to wish you all a peaceful and prosperous 2021. Okay, so we're continuing with our series on implementing a linear algebra library in C++, and in this episode we're going to continue with looking at how to compute the matrix rank. If you recall back from the previous video, we looked at how we can compute the matrix rank by counting the number of non-zero rows left in our matrix after we've performed Gaussian elimination to convert it into row-echelon form. But we saw then that there are some conditions where converting to row-echelon form doesn't work, and at the time I talked about how it's possible to then compute the rank of the matrix by finding the largest non-zero submatrix with a non-zero determinant, and that's exactly what we're going to look at today. Okay, so I don't want to make a long introduction, but just quickly say before we jump into that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel and hitting the bell icon for notifications so that you don't have to miss any future videos. I do try and make a video roughly once a week. That's slipped a little bit over the holiday season, and obviously for people that are regulars to my channel, you'll see I'm in a different location now, so I have been traveling. We'll talk about that a little bit later. And yes, if you subscribe, you don't need to worry about missing any episodes. Thank you very much. Right, without much further ado, let's jump straight in and let's look at how we can compute the matrix rank by finding the largest non-zero submatrix with a non-zero determinant. So, in the last video, we saw how a system of three equations and three unknowns can be illustrated by a set of three planes. And we saw that when such a system has a solution, that solution corresponds to the point at which all three of those planes intersect. In this example here, we see that this system of equations has a solution at x equals 4, y equals 1, and z equals -6, and we can see how the three planes all intersect at that point. We then went on to discuss what happens for systems of equations that do not have a solution, and we showed three different examples of what that might look like geometrically. Firstly, we saw an example where the three planes all intersect with each other, but not all in the same place, as shown here. Secondly, we looked at an example where the three planes are all parallel. This system would obviously have no solutions. And finally, we looked at an example where the three planes all intersect with each other along a line, giving a system which would have an infinite number of solutions, or as we say mathematically, no unique solution. We then went on to look at how we can use the rank of a matrix to determine whether the system of equations will have a solution or not, and we looked at how we can compute the rank simply by counting the number of non-zero rows after we have performed Gaussian elimination to reduce the matrix to row-echelon form. However, we also saw that there are some cases where Gaussian elimination is unable to completely reduce the matrix to row-echelon form, and therefore we cannot use this method to compute the rank. I mentioned then that the other way to compute the rank is by finding the dimension of the largest non-zero submatrix with a non-zero determinant, and that is what we're going to look at in this video. An example of such a matrix may be seen here. We cannot use Gaussian elimination to reduce this matrix to row-echelon form, so we have to use the determinant method to compute the rank. In this case, we can see that as rows 1 and 3 are the same, but row 2 is different, the rank of this matrix should be 2. So, to do this, we are going to extract each possible submatrix and compute its determinant. If that determinant is non-zero, and the submatrix doesn't contain only zeros, then the number of rows of that submatrix is equal to the rank of the original matrix. In this case, we find that the first submatrix, as shown in orange, for the element shown in blue, when we compute the determinant of this submatrix, the result is 0. So we move on to the next submatrix. Now, looking at the submatrix shown in orange for the element shown in blue, we compute its determinant as before, and we get a value of 1. This is therefore the largest submatrix with a determinant that is non-zero. Thus, the number of rows in this submatrix, which is 2, gives us the rank of the original matrix. We keep going with this process until either we have tested every submatrix, or we find one which is non-zero and has a non-zero determinant. Obviously, in this example, we would stop after the second submatrix, but I've added one extra step just to illustrate the process. As we said at the beginning of this example, we can see that the rank of the original matrix is 2. Therefore, we can see that this process gives us the right result. Let's take a look at an example for a larger 4x4 matrix. So, in this case, we start by finding the submatrix for the first element, just the same as we did for the 3x3 example. Now, of course, the submatrix will be 3 by 3, one row and one column less than the original. If we compute the determinant for this submatrix, we get a value of 0, so we have to proceed to the next one just as before. Except we do one extra thing. Now we store the 3 by 3 submatrix that we have just found into a vector of QB matrix 2 objects. We will see why we do this shortly. We then proceed to the next element in the original matrix and extract the submatrix as shown here. Again, we compute the determinant for this submatrix, and it also has a determinant of 0. So we add that submatrix to the vector just as we did before, and we keep going. We do the same thing for the third element, and we find that the determinant of the submatrix is also 0. So we add this submatrix to the vector as before. And we keep going through all of the elements of the original matrix until either we find a submatrix with a non-zero determinant, or until we have checked every 3 by 3 submatrix. Once we have completed all the 3 by 3 submatrices, we will have a vector that contains every 3 by 3 submatrix from the original. We now proceed by taking the first element from this vector, which corresponds to the first 3 by 3 submatrix that we found. We then delete this element from the vector, and then proceed to extract the 2 by 2 submatrix corresponding to the first element of the 3 by 3 matrix. We then compute the determinant of this submatrix, which in this case gives a value of -20. As this is non-zero, this is where we would stop the process. The number of rows of this submatrix is 2, and therefore this is the largest non-zero submatrix with a non-zero determinant. So we know that the rank of the original matrix must be 2. Now, let's suppose just for example that the determinant of this submatrix had been 0. In this case, we add the 2 by 2 submatrix to the vector of matrices that we are building up, and then we proceed to extract each remaining submatrix from the 3 by 3 matrix until either we find one which has a non-zero determinant, or we look at all of the submatrices for this 3 by 3 matrix. In that case, we move on to the next 3 by 3 submatrix from our vector and repeat the process. Once we get down to the 2 by 2 matrices in the vector, we don't need to compute any more submatrices, so then we just compute the determinant for each one. And that is the whole process. I think if anything about that is not clear, it will become clearer when we come to actually look at the code. It isn't as actually complicated as it may sound, as I think you will see. So let's jump right in and have a look at how I've gone about implementing this algorithm in C++. Okay, so here we are looking at the code. Now obviously I've gone ahead and I've put the code to compute the rank in the QB matrix class that we've been working on all along. Indeed, in the last episode we already looked at how to compute the rank using the Gaussian elimination method, so we have already put that code in here. Now there's a couple of extra functions that I've also added that I just wanted to talk about that we need in order to be able to support what we want to do. The first of those is that I had to overload the equals operator, which we can find here. So I've added code to overload the assignment operator, technically it's called. What I want to do actually is to talk about that in a future video, about when and why it can be necessary in C++ to overload the copy constructor and also the assignment operator. Now I should really have done this at the beginning when I first made the video about the QB matrix class. I thought to overload the copy constructor, but what I didn't think to do was to overload the assignment operator, and that can actually be really important. But like I say, I think for a future video I'll do an episode specifically just on copy constructors and assignment operators, because it's quite an interesting thing and it's really important in C++ to get that kind of thing right. But we'll have a look at the code for that in a moment. The other thing that I've added, of course, we have our function to return the rank, which is naturally always an integer, and I've added one more function here which returns a boolean, which is called is_non_zero, and this is simply a function that returns true if at least one element in the matrix is not equal to 0, and otherwise it returns false. So let's have a look at that first, is_non_zero, which should be down here at the end somewhere. Where are we? Here we go. So here we are, function to test whether the matrix is non-zero. So we have bool QB matrix 2 type T : is non-zero, and we simply loop through every element using m underscore n elements, and we just check if the element there in m matrix data I is close enough to 0. We've talked about the close enough function before, I'm not going to mention it again, and if so we increment our non-nonzero counter, and then we simply return a test of whether the non-nonzero counter is equal to 0 or not. Now this could actually be done more efficiently. I mean, obviously the first time we encounter an element that is not 0, we could actually stop the loop at that point. There's no point really going through every element, but that is how I've done it. I may well come to refactor that code in the future to be more efficient. Anyway, let's have a look at the overloading of the assignment operator. So that will be up at the top, overloaded operator functions, multiplication. There's a lot of code for that one. The equality, here we are, the assignment operator here. So all we're doing is we accept as input a const reference to a QB matrix 2 object, and we're going to return a QB matrix 2 object. And the first thing we need to do is we need to test that we're not assigning to ourselves. So we do if this is not equal to, and a reference to the right hand side, so if the this pointer is not the same as the pointer we have here, then we proceed. That's important in case the user, someone writing code, may have made a reference to ourselves, so if in that case we don't want to do anything. We then copy the number of rows, the number of columns, and the number of elements from the right hand side matrix, and then we need to see if we already have data assigned in the matrix that we're assigning to. We want to delete that, okay? And then we reallocate m matrix data to the new number of elements, and then we simply loop through all of the elements and we copy them from right hand side m underscore matrix data into m underscore matrix data over here, and then we simply return the value pointed to by the this pointer, return star this, and that's everything that we need. You'll see that that code is actually very similar to what we wrote for the copy constructor before, but just a tiny little bit different. And as I say, I'm probably going to do another video where we talk about assignment operators in much more detail and why they're necessary. But for now, let's just say that it's necessary to overload the assignment operator to make the code for computing the rank that I've created actually work. And one other last thing that I have changed since the last video was in the class destructor. Where are we? Here we go. So I changed this a little bit. So rather than testing if m underscore matrix data is equal to null ptr, I've simply set if m underscore matrix data. Then, so if we have data, then we delete it, and then we specifically assign a set m underscore matrix data equal to null ptr when we've finished. Okay, so that's basically all of the housekeeping stuff that I've done. Let's have a look at the algorithm for computing the matrix rank. Let me just find it. We're getting quite a lot of code here now. We're pushing over 1,000 lines of code in our matrix class. Here we go. Compute the rank of the provided matrix. Okay, so as before, we do template class T because we don't know in advance what type of class the user will have put values into this matrix of. We return an integer. We've really talked about that before, and the first thing we do, of course, is we make a copy of the matrix so that we don't accidentally modify anything. And yes, the first thing we're going to do, as we talked about in the previous video, is then convert that matrix into row echelon form. And we went on to talk about that before, and we looked at this code here that then simply counts the number of non-zero rows. Now the new condition that we're writing code for today is for the condition where the converting to row echelon form does not work. So if we fail our is row echelon test, then we're coming into the new code that we've written today. And this may have seemed really quite complicated in my explanation of the algorithm before, but I think you'll see from the code it's really not that bad. The first thing that we do is we set up an std vector class of type QB matrix 2 of type T objects called submatrix vector. So this is the vector into which we're going to store the submatrices as we go through the process. The very first thing we do then is we need to store the matrix that we're starting with, okay, which is the this matrix, or indeed matrix copy. Yeah. No, yes, it makes sense because we failed our process to convert to a row echelon form, so we might as well use the matrix that we're working with. That's what I was thinking. So we take the value pointed to by the this pointer and we push that back into submatrix vector. We're then going to loop through the submatrix vector until either we have tested every submatrix or that the complete flag has been set. So first of all, obviously we set a boolean called complete flag to false, and we initialize submatrix count to 0. And then we're going to loop while submatrix count is less than submatrix vector.size and complete flag is false. So the first thing we do, we extract the current matrix that we're going to be working with. So we create a new QB matrix 2 of type T object called current matrix, and we set that equal to submatrix vector at submatrix count, which of course starts from 0, so to begin with that's going to be the first one. We then increment submatrix count by 1. And then we're going to test if that matrix is non-zero. We're only interested in matrices that are non-zero, so this is where we use the isNonZero function that we just talked about. So assuming that the current matrix is non-zero, we come into this part of the code and we compute the determinant, which gives us a value of type T. Current matrix det is equal to current matrix dot determinant, and then we test if that determinant is not close enough to 0. If it isn't close enough to 0, i.e. it's non-zero, we set complete flag to true, because this is the point at which we can stop the process, and we set non-nonzero rows, which is the variable we're using to store the rank, that's to be compatible with the code that we talked about last time, equal to simply the number of rows in current matrix. As we just saw in the slides that we were looking at, the rank of the original matrix is equal to the number of rows in the largest non-zero submatrix with a non-zero determinant. So where it gets interesting is if the current determinant, here current matrix determinant, does pass the test for being close enough to 0. Now in that case what we're going to do is extract and store each submatrix from that matrix, providing that they're larger than 2 by 2. So we determine first of all that the submatrix we're dealing with is going to be larger than 2 by 2. And then we simply loop over every element of that, for I equals 0 to num rows, for j equals 0 to num cols, and then we extract the submatrix corresponding to that element and store it into our vector. So we see that we're going to take current matrix, and then we're going to loop through every element in current matrix, find the submatrix for that element, and push that back into our submatrix vector. And then simply we come back to the top of this loop, the while loop, and then we extract the current matrix again, and of course we've incremented submatrix count, so now we're going to take the next matrix in the vector, and so on. And we simply repeat that process until either we reach a condition where we find a non-zero determinant, or indeed we just drop through and we don't do anything to non-zero rows, which would then come out at 0, and we give a rank of 0, which would be, in that case, the right result. And that's actually it. Now, as I said, I did tell you it's actually perhaps it's not as complicated as it sounded looking at the slides, but I think taking the slides and the code together should give a really good view of how everything is working. Okay, so let's have a look at how we've gone about testing it. So if I go to testcode_qblinearsolve.cpp, this is the code we wrote before to perform testing of the qblinearsolve function. So I'm not really going to talk about all the stuff that we did before. I'm just going to talk about the new bit, which is down here, that I've created here for testing computation of the matrix rank. So we display to the user that that's what we're going to do. And we start with testing a solvable system. So we take the A matrix that we defined previously. Let's just have a look at that. That will be up here at the top somewhere. Here, so A mat is a 3 by 3 matrix constructed out of this data that you can see there. And we're going to look at computing the rank of that. So we simply use cout rank equals, and then we do amat.rank, so that will call the rank function. Now, of course, that's a solvable system, which means it's amenable to reducing to row echelon form by the process of Gaussian elimination, so that's not going to use the new code that we wrote today. We then test with an unsolvable system, which we use amat5, which comes from up here. amat5 is this one, it's again 3 by 3, and we're using this data 3, 1, 2, 5, 3, 6, 2, 2, and 4. Now this is an unsolvable system, okay, and we then compute the rank of that, and we see what the result of that will be, and then we also display that in row echelon form. I did talk about those two tests in the previous video, and we see that in the second case the rank is less than a number of rows, indicating that there's no unique solution, and we can see that from the determinant as well. Now the interesting bit is here when we come to test the condition when Gaussian elimination fails. Okay, so here we set up a vector of doubles called G fail data for a 3 by 3 matrix, and this is the example that we saw before, 0, 0, 1, 1, 0, 1, 0, 0, 1. So the first and the third rows are identical, and obviously this system has no unique solution, and very clearly is also not going to be amenable to reducing to row echelon form by Gaussian elimination. Okay, so this makes a very good test case. So we display what we're testing with, and then we attempt to perform Gaussian elimination to see what that gives, and we display that result, and then we're going to attempt to compute the rank. So we call fail matrix.rank, and that will attempt to compute the rank. And because this matrix is not amenable to Gaussian elimination, that will use the new code that we've created today, and we test that that gives us the right value. And then we also go on to test with a matrix containing only zeros, and we look at the rank of that. And we test with also a larger matrix here, to coefficient matrix, which is, yes, we formed that from the random one. So we test with the larger 10 by 10 random matrix that we formed before, and we compute the rank of that. And that's the basic testing that I have done. Now, I have gone through and tested this also with other software to make sure. I believe that everything works as it should. If you implement a version of this code yourself and you test it and you find any problems, do let me know. Obviously, I offer no guarantees that it is without errors. There could be problems. The testing I've done indicates, however, that it should work as intended. Okay, so let's have a look. Let's go to our terminal window and let's have a look at what we get when we compile this code. So the first thing we need to do, of course, is compile the g++ -o, and we're test code underscore qb linear solve, and our file is test code underscore qb linear solve .cpp, and I always use -std equals c++ 17. Okay, so let's compile that. Okay, and let's run our code, test code qb linear solve. Okay, and okay, we're going to have to expand my terminal window a little bit so we can see that better, but let's just have a look, and we're just going to look at the new conditions. Okay, we looked before, everything with solvable systems works and the unsolvable system. So just actually I will mention it. So for the 3 by 3 matrix here, we get a rank of 3, where 3 is equal to the number of rows, so obviously that has a solution. The unsolvable system we looked at gave us a rank of 2, and that's the original system there, and if we convert to row echelon form, we see that that doesn't work because that row is all 0. Okay, so what's more interesting and what uses the new code that we've created today is we're testing the condition when Gaussian elimination fails, and we test with that matrix. We attempt to perform Gaussian elimination, but simply doesn't do anything. If we attempt to compute the rank of that, we get a value of 2. Now that is the right answer because the first row, the first row and the second row are different, and also the second row and the third row are different. So this matrix, it could be said, has 2 degrees of freedom. The rank is 2. Okay. Okay, and if we test with the 0 matrix of all zeros, we get a value of 0, which is the result that we want. Okay, and then we test with the larger example, the big random 10 by 10 matrix, and that gives us a rank of 10. Now, of course, that didn't use the new algorithm to compute the rank there. If we really wanted to do that, we can. We can go back to QB matrix class, and we have the test here where we're computing the rank. Here we go. If the matrix copy is not row echelon, then we conduct this code. If we comment that out and simply put if true, like that, okay, just doing this just for example, that will force it to use the new code to compute the rank in every case. Let's save that. And this is a good idea to do because it allows us to test whether our code is actually working even more thoroughly. So let's compile that and we'll run it again. Okay, now you see that took quite a long time to compute the rank for the 10 by 10 matrix. There was a noticeable pause there, and that is not just because I've got my screen recording software running at the same time. That really, it is actually quite inefficient, but it gives a rank of 10 for that large matrix that we want. It gives a rank of 0 for the 0 matrix, a rank of 2 for that unsolvable one, and then we come back up to here. We also get a rank of 2 for that one, we get a rank of 3 for the original solvable system, and so on. So we can see quite clearly that the new code does indeed work. And of course, before we finish, let's just put that back as it was. So the reason that we implement both methods, just in case you're wondering, is that as we've just seen, the method using the determinant, finding the largest non-zero submatrix with a non-zero determinant, is actually quite a lot slower than the method of counting, using Gaussian elimination to convert the matrix to row echelon form and then counting the number of non-zero rows. So it's best to write code to implement both methods. We use the fastest one if we can. If that fails, because for some reason we can't convert the matrix into row echelon form using Gaussian elimination, then we drop back to trying to find the largest non-zero matrix with a non-zero determinant. And there we go. That's all of the code that I wanted to talk about today. Okay, so that's everything I wanted to talk about today. We've looked at how we can compute the rank of the matrix by finding the largest non-zero submatrix with a non-zero determinant, and we've talked about how we can implement that algorithmically, and we've gone on to look at how we can actually create that in C++ code. The algorithm that I've implemented also required implementing a overloading function, a function to overload the assignment operator. And as I said in the bit when we were talking about the code, I want to do another episode, probably at some point in the not too distant future, to talk about when and why it's necessary in C++ to do things like overloading the assignment operator, and why simply having the overloaded copy constructor as we had before in the QB matrix class wasn't enough. Anyway, that's, as I say, really everything I wanted to talk about today. So I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked it, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Anyway, listen, it's been a pleasure, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.